Hello everyone, my name is Norbert Ludant. I am a PhD student at Northeastern University, and I am going to present our work, which introduces a novel attack capable of linking BLE advertisements to long-term identifiers and the implications of given attack. This work was carried out with Tianfo Hu, Shashank Narain, and Gebranovir. First of all, Bluetooth is a technology that is everywhere around us. Since Bluetooth was first introduced back in 1998, the number of Bluetooth devices deployed has continuously increased. It is forecasted that by 2024, annual Bluetooth-enabled device shipment will exceed 6 billion. This includes Bluetooth Low Energy, a technology introduced as part of the Bluetooth 4.0 core specification. One of the novel key features included in BLE is the concept of advertisements, which consists in broadcast transmission by Bluetooth devices, for instance, offering a service. BLE advertisements are widely used, not only by IoT devices due to the lower power consumption, but also by smartphones, laptops, or any other Bluetooth devices. Although multiple attacks on BLE privacy has been shown, most are due to an improper implementation, and BLE advertisements have been considered secure from a linkability point of view, in the sense that a passive attacker cannot link BLE advertisements to a specific device if all parts are implemented correctly. This is due to the use of frequent periodical MAC address randomization. In fact, multiple privacy-preserving protocols built on top of this assumption for their BLE-based system, such as digital contact tracing apps. Additionally, recently it has been shown that Bluetooth Classic transmission can be linked to a global identifier by a passive attacker listening to the Bluetooth spectrum, something that was believed to be hard to achieve. This finding, together with the proliferation of multiple services relying on BLE and linkability, such as contact tracing, raised a question for us. Can BLE advertisements be linked to a long-term identifier? This motivation led to an interesting finding. A vulnerability in Bluetooth chipsets allows an attacker to link a BLE advertisement transmission to Bluetooth Classic transmissions coming from the same device, and in turn, to a long-term identifier, Bluetooth address. We'll show in the presentation how it's possible to exploit this attack across different devices and scenarios with high reliability. The presentation is structured as follows. First, some useful technical background about BLE and BTC will be provided, which will aid in understanding why the vulnerability exists, along with the explanation of the full system we implemented for the attack. After that, we'll describe the implications of given attack for privacy-preserving protocols, and we'll add some examples. The implementation setup and results section will describe our measurement campaign and summarize our findings. Lastly, I will describe the mitigations we implemented for Android devices in the Countermeasures section. First, to understand to attack, it's important to know a few concepts of Bluetooth Classic. Bluetooth Classic operates in what is termed as piconnects, where there is a master device and multiple slaves that are synchronized to the master clock. In time domain, Bluetooth Classic is divided in time slots of 625 microseconds. And although packets can span multiple slots, as we see in the figure below, any packet is always aligned to a 625 microsecond slot. As for BLE, it has similar physical layer characteristics, operates over the same bandwidth as Bluetooth Classic, and uses frequency hopping as Bluetooth Classic. Focusing on BLE advertisements, they're transmitted within what is called an advertising event. In each advertising event, the advertisements are transmitted in 3 different advertising channels. As we can see in the scheme below, 2 consecutive advertisement events are spaced by some advertising interval plus a random delay added to avoid collisions. Interestingly, the duration of the advertising interval is a multiple of 625, just like the Bluetooth Classic bandwidth. Now that some details for Bluetooth have been described, it's time to answer the question: how can a passive attacker link BLE advertisements to Bluetooth Classic packets? Our initial guess was that given the similar frequency hopping pattern of Bluetooth Classic and BLE, shared characteristics, and the high integration of Bluetooth system on chips, it is likely both radios are driven by the same clock. To confirm our hypothesis, we took measurements of the timestamps of BLE and BTC packets coming from the same device, and computed how tightly aligned they are in time. On the right, we show these results as the time offset in microseconds between BTC and BLE packets. The top figure corresponds to BTC and BLE packets coming from the same device, whereas on the bottom, the transmissions are coming from different devices. Initial results show that, in fact, both transmissions, BLE and BTC, coming from the same device, seem to be synchronized to the same time slot of 625 microcycles. But the results are noisy and there is multiple constant offset values. For instance, on the top right figure, we see many packets with very small time offset difference, meaning they are quite aligned, and values with 100 of microsecond mismatch for the same advertisement. This makes it hard to discern the two cases where linkability exists and not, and makes it hard to create metrics that are accurate separating the two cases. The problem arises, first of all, due to the effect of the wireless medium, and to some extent by hardware imperfections. But peculiarities of BLE advertisements play also an important role. For instance, we find that not all advertisement channels exhibit the same time offset, and sometimes this value is both device-dependent and advertisement configuration-dependent. It is required to develop an inference algorithm that we integrate in our full system. To solve all the challenges encountered from RF sampling to linking, we carefully design a full attack system that tackles all the challenges with different blocks. First, our system receives the radio frequency IQ samples through a low-cost software-defined radio, for instance, a USRP B210, and decodes the samples to simultaneously extract information of both BTC and BLE transmissions. For Bluetooth Classic, this includes the global Bluetooth address and the timestamp of each packet received. For BLE, the information includes the BLE advertisement itself and the timestamps. As the collected information is noisy, it is required that it is processed, sorted in channel, and then processed to derive an alignment quantification between the clock of Bluetooth Classic and the clock of BLE, between each pair of Bluetooth addresses and BLE advertisements. This block is handled by the data processing block. Finally, the inference algorithm computes the time alignment between BTC and BLE, addressing the peculiarities of BLE such as irregular channel offsets, and outputs if the BLE advertisement is linked to any Bluetooth address and which. With this system, we are able to reliably link BLE advertisements to Bluetooth Classic transmissions for multiple scenarios, as we'll see in a moment. But first, now that we have presented the attack, it is important to understand that the linking of BLE advertisements to a device address breaks the assumption that BLE advertisements cannot be linked. And also, equally importantly, it breaks a key assumption of privacy-preserving BLE-based protocols, as most explicitly rely on the linkability through macro-randomization of BLE advertisements. Furthermore, linkability of communications can not only enable tracking by itself, but can also be used as a crucial stepping stone for more sophisticated attacks. Two examples of privacy-preserving protocols that rely on BLE advertisements are contact tracing apps and Apple Find My. In case of contact tracing apps, most rely on the exposure notification service developed by Google and Android. For the exposure notification service, the BLE advertisement data consists of the rolling proximity identifiers broadcast by the user devices. These proximity identifiers are generated such that they do not reveal the user's identity. However, with the vulnerability we expose, it will link them to the Bluetooth address. Then, an adversary that periodically downloads the diagnosis key can then generate the proximity identifiers of infected users and compare them to proximity identifiers previously recorded and linked to Bluetooth addresses. This does not fully de-anonymize infected users. However, it can serve as a stepping stone if it is combined with any other side channel that links the Bluetooth address to users' private information. In order to determine the scope of the attack, we carry out extensive measurements to understand the impact across different variables: exposure time to the attacker, different target devices and apps, density of devices, wireless traffic, distance, and mobility. To do so, we evaluate the attack over 5 test devices, both Android and Apple, and 4 phone apps: contact tracing-based, Apple Find My, and a BLE advertising app. We take measurements in 3 scenarios: a residential area with low to average traffic, an office environment which exemplifies a high traffic area as it includes 2 IT labs and more than 100 BLE advertisers. And lastly, due to the limited physical space in the previous scenarios, we carry out measurements in a football field to measure the performance at a distance and with mobility. Our results show that the attack proves to be highly reliable and robust across devices, models, and chipsets. The table below, for instance, indicates the probability of linking correctly a device in a low-density scenario, where there is 20 other BLE advertisers. Our system is able to link correctly, consistently for 10-second recordings, but even 1-second recording succeeds more than 85% of the time. Our results indicate that the probability of linking correctly a device is already above 90% for 10-second recording in most scenarios. As for different apps, we find that the probability depends on the BLE advertising configuration. In this way, advertisements transmitted with higher power have a higher probability of linkage as they are more likely to be decoded. For instance, the Apple Find My app uses high transmit power, and although the advertisements occur less often than for other apps, only every 2 seconds, it is more vulnerable to the attack than apps using, for instance, the exposure notification service on Android, which transmits at a very low power. For challenging scenarios, such as crowded scenarios, the probability of linking BLE advertisement with same device Bluetooth Classic transmissions is between 80% and 95% depending on the app, with more than 100 BLE advertisers and significant congestion in the scenario. Another challenging scenario is when a Bluetooth Classic connection on a device is idle and just transmitting sporadic keep alive messages. In this scenario, an attacker is able to correctly link BLE advertisements 90% of the time for 10-second recordings. As for measurements related to spatial consideration, we find that it is difficult to exploit the attack for most apps at distances over 80 meters and as movement speed increases. We find that Apple devices are still more vulnerable even in this scenario because of the high transmit power. But it's harder for apps that transmit at lower power. We can see that exemplified in the table when we compare the same app for Android and iOS. In light of the results during our experiments, we propose, implement, and evaluate a set of effective countermeasures for Android. As the vulnerability is deeply rooted to the chip, we believe that eliminating this attack will require significant changes to the Bluetooth Classic and BLE chipsets. However, we provide a set of countermeasures that aim at reducing the efficacy of the attack. We focus our countermeasures on ideas that can be implemented for the Android OS to reduce attack performance. As we have seen, even if Bluetooth Classic is on but only paired, the linkability attack is still possible. Then, the best idea is to disable Bluetooth Classic when it's not being actively used. As this is sometimes not possible, BLE advertisements transmit power should be kept to a minimum to reduce the range of the attack. To do so, we develop a system on Android that first controls the Bluetooth Classic and BLE state, turning off or on each one independently, dependent on the connection status. For instance, if Bluetooth Classic is not actively used, our system turns it off. This is not trivial because in the Android Bluetooth stack, both Bluetooth Classic and BLE are controlled by the same API, and BLE cannot work without Bluetooth Classic, so we have to decouple both states. Secondly, we limit the Bluetooth transmit power when Bluetooth Classic is on, and lastly, our system periodically reduces the transmit power of BLE to try to make a passive attacker lose synchronization. In order to implement the last two measures, as we are not able to change the BLE transmit power without changing the functionality of the app, we need to find a workaround around this issue. We validated the library by implementing a BLE advertiser app without using any Bluetooth Classic code and observed that it works reliably. Also, to verify the mitigation system, we loaded it on a Google Pixel smartphone and performed measurements, showing that the attack is indeed effectively reduced. Thank you very much for listening.